Thank you for coming to our meeting today. In regards to you can do data science in a GUI with Hadley Wickham, Chief Data Scientist at RStudio, as well as the member of the R Foundation and an Adjunct Professor at Stanford and at the University of Auckland. He builds both computational and cognitive tools to make data science easier, faster, and more fun. His work includes various packages as well as principled software development. Also, he enjoys writing, educating, and speaking to promote the use of R for data science, and you can learn more from his website. So please help me to give a very warm welcome to Hadley.
Good evening. So tonight I've kind of given you a deliberately, provocatively titled talk to hopefully entice you in here, but hopefully there won't be too much that you disagree with in my talk. So I'm going to talk about kind of my beliefs about data science, some of the tools that I've worked on. But before we can do that, I think it's really useful to talk about what is data science? There's now approximately 1 billion different Venn diagrams showing you what data science is. But to me, I think the definition is pretty simple. Whenever you're struggling with data, whenever you're trying to understand what's going on with data, when you're trying to turn that raw data into insight and understanding or discoveries, I think that's data science. I'm not going to be too interested in the philosophies of data science. What I am more interested in are what are the tools of data science? What do you need in order to actually do data science? And so before I go on, I have a few questions for you all just to get a little of a sense of kind of what sort of people you are. So how many of you would say you're a data scientist? How many of you would identify as a data scientist right now? Okay, awesome. And how many of you would identify as a programmer? Okay, those are not mutually exclusive. And how many of you have used R before? Okay, that's awesome. And how many of you have used Python before? Okay, pretty much everyone. Okay, awesome. So I'm going to kind of talk about the tools of data science. I'm going to talk a little bit about why I think, you've kind of all used R and Python before, so in some sense, I think maybe you're already convinced at least a little bit. I'll talk a little bit about some of the reasons that I think using a programming language to do data science is so important, so much more important than using a GUI. And then I'll talk a little bit about my favorite programming language, R, and then some of the tools that I've worked on, these domain-specific languages, which help you express the ideas of data science more easily. So to me, there are a few main tools of data science. The first one, obviously, before you can do anything, you have to get the data out of whatever crazy format it currently is into your data science environment. Because sometimes this is reading CSVs, sometimes this is loading from a database, but this might be scraping websites, calling APIs, whatever, you've always got to get the data in first. And I'm not going to talk too much about import tonight, because in my experience, data import is either 80% of the time it's just incredibly boring, and the other 20% of the time is endless screaming. And neither of those make for fantastic talks. So I'll talk a little bit about that, but I'm not going to focus too much on that tonight. One thing, once you have imported your data that I think is really important, is to do what I call tidying your data. This is not cleaning your data where you care about are the values accurate. Tidying your data is just about getting it into a structure that is going to enable the rest of your analysis. Once you've done that, then your job as a data scientist is to understand what the heck is going on in your data set. And I think there are kind of 3 main tools that help you do that. You're often going to need to do some fairly kind of mechanical transformations. You might summarize multiple values down to a summary like a mean or a count. You might create a new variable that's a function of existing variables. I think of these as transformations. They're really, really useful, but they're not very sexy. So to me, there really are two main engines that help you understand what's going on in the data set. Visualization and modeling. And visualization is like fundamentally a human activity. This is figuring out how can you take the best advantage of the innate skills of psychology, that looking at things and understanding what's going on. So visualization is fundamentally a human activity. You look at a plot and it gives you some insight into what's going on. And visualizations are great, particularly great for two reasons. First of all, you can go to a visualization with a pretty vague question, and you can use the visualization to help you refine your question. And often this is a big part of the challenge of data science, is taking that vague, ill-formed question in your head and trying to make it sufficiently precise that you can answer it quantitatively. The other great thing about visualizations is that you can see something that you did not expect. They can surprise you. But the downside of visualization is because there is that human in the loop, they don't scale particularly well. As you get more observations, as you get more variables, you simply cannot look at every possible visualization. And so to me, the complementary tool to visualization is modeling. And I think of modeling very broadly, but basically whenever you can make your question sufficiently precise, you can answer with an algorithm or with some summary statistic. I think of this as a model. And models are great because they are fundamentally computational. And even if they're slow, it's way easier to throw more computers at a problem than it is to throw more brains at a problem. But the problem with models is that every model makes assumptions, and a model by its very nature cannot question those assumptions. So at some fundamental level, that means a model cannot surprise you. So this is why I think visualization and modeling are such great complementary tools. Visualizations can surprise you, but they can't scale. Models scale much better, but they can't fundamentally surprise you. So in any data analysis, any data science project, you're going to loop through these things again and again and again. You're going to use visualizations, look at maybe a small subset of your data set, use that to generate hypotheses, make those concrete and quantitative and precise, then use models to scale them up to a much larger subset of your data. Now you're going to work through this loop again and again and again and again until you have decided that you're done, that hopefully you haven't tortured the data until it's confessed. Hopefully you found some real signal in the data, and then you're going to do one of two things. You're going to have to communicate those results to another human being, whether that's your boss or your supervisor or some other decision maker inside your organization, or you're going to want to communicate those results basically to another computer. You're going to want to think about, how do I deploy this in some sort of automated way? So in some sense, this is, I think, a little bit of the division in my mind between kind of classical statistics and data science. Classically, statisticians would be more concerned about how do we get humans to update their beliefs, and a big part of data science today is how do we plug models into these computational pipelines, where now the visualizations are no longer the end point, but they're a beginning of some other pipeline. And so a lot of my work has been developing tools to make each of the parts of these processes easier in R, and the so-called tidyverse, which we'll come back to a little bit later on. So if you're going to do data science, why should you program? Well, to frame that, I think it's useful to think a little bit about, well, what do you have to do when you're solving a data science problem? Obviously, you have to use a computer in some way, right? Maybe 30 years ago you could do statistics with pencil and paper. That's just no longer possible today. There has to be a computer involved somewhere. And so what you have to do is you have to first think about what you're going to do. The computer is never going to tell you. Then you have to describe what you want precisely in such a way that the computer can understand, and then the computer has to go and actually do the computation. And so there's two extremes to this. So one extreme is a sort of GUI, SPSS type approach, where you just point and click everything is laid out in front of you, all of the options are laid out in front of you, which is great because you can see everything you can do, but it's also terrible because you're constrained. You can only do what the inventors of SPSS wanted, or SAS or Excel wanted you to do. Whereas R is kind of any programming language is kind of the opposite. All you get is this blinking cursor. It's just sitting there. You can do literally anything, but it's not going to give you much help. So I think of this. So to me, the important thing about programming languages like R and Python is the language part. They give you a language to express your ideas. They give you very few constraints, which makes life tough when you're learning or if you only do data science occasionally. But the payoff for investing in a programming language is you get this new language in which you can express your thoughts. Now the other thing that I think is really great about programming languages is that you interact with a programming language with code. And code is just text. And there are two amazingly powerful workflows that text gives you. The first workflow is copy and paste. Now, you all laugh, right? Like, copy and paste is not like a strategy that you want to like carry you throughout your entire career, but it is an incredibly powerful strategy to like repeat yourself. When you need to do something multiple times, if you can copy and paste, like, it's not the best solution in the world, but it's going to get you there. It's a great scaffold. And the other great workflow it gets you is Stack Overflow. Right? Because code is just text, you can dump your error message, you can stick your error message into Google, and Google will lead you to Stack Overflow, which will solve your problem for you. Right, again, this is a little humorous, but I do think this is important, right? Because code is just text, this means you can put it in an email, like you can tweet it, you can Google it. There's a huge amount of power associated with that expressing your ideas in text, because we have so many tools for working with text. And there's also a bunch of great tools around the provenance of text. That text is kind of reproducible, like when you've expressed your ideas in code, you can rerun that code with new data later on and get updated results. There's lots of great techniques for seeing the differences between two pieces of text. You can read text. It's not some like crazy opaque binary format. You can look at it, and even if you don't know the programming language, even if you don't know exactly what that code is doing, you can puzzle out, you can understand the intent behind it. And then that also allows us, we can host code in all sorts of ways to make it open and share it with others. And so I wanted to give you just a couple of little examples of that from GitHub. So the first one is, this is a project from British Columbia that for computing population estimates. They've done all of this work in the open on GitHub. So this is their GitHub repo. And one of the neat things about putting your data analysis into a system like Git, using a tool like GitHub, is not only do you get to see where the analysis is now, you get to see how it has evolved over time. You get to see these series of commits showing what has gone on over the process of the analysis, and you can drill down into one of those commits, and this is probably hard for you to read, but you can see like what exactly has changed. Well, in this case, we're just changing the colors of a bar chart. It's not like super exciting, but this ability to see what has changed is incredibly powerful. You can not only see like where data analysis is now, but you can see how it evolved over time. A related set of tools are these tools known as R Markdown, which allow you to mingle R code and text to produce a single output. Plenty of other similar tools exist for other languages. I want to show you a little example using R Markdown. This is from my colleague Jenny Bryan, who is doing a data analysis of the Calaveras Jumping Frog Jubilee. So this is a state county fair, I think, where they have a frog jumping competition. So the purpose of an analysis is mostly to kind of, as an example, to teach with. But one of the things I think is neat about this is that in the README, which GitHub exposes very nicely, Jenny has shown some of the summary statistics, or actually just shown this data frame. So this is the README. When you go to this GitHub site, you get this nicely formatted HTML page, web page. You can see what's going on. How was that generated? Well, this comes from an R Markdown document. The R Markdown document has text. At this point, all we know that each frog is one frog job. And we've got some R code in there as well. And so we can run that R code, intermingle it with the text, and we get a beautifully polished HTML document like this. And we can go back even one step further. How do we do this nice formatting? How do we get these headings? Well, R Markdown uses this plain text format called Markdown. You just write text in a fairly, pretty simple set of conventions that can then be nicely converted to HTML. So this whole R Markdown workflow, I think, is really important because you're no longer like copying and pasting like graphics from one thing and sticking them into your Word document, and then your data changes, and then you've got to like carefully rerun your analysis, and then carefully copy and paste exactly the right images into exactly the right space. Every time you have to do something by hand, every time you've got to copy and paste by hand, you've got that possibility of error, and ideally, you really want to avoid that. And then kind of one of the things, like on the flip side, like one of the things that kind of gives me nightmares is like this dialogue in Excel. So what's happened, I've selected one column, I want to sort by that column, and Excel gives me this option. Do I want to expand the selection, or do I want to continue with the current selection? And what these options really should be, it should be, what do you want to do? The right thing, or basically randomize your data. And so it's kind of not, like it's moderately horrifying that Excel lets you randomize your data, basically if you click the wrong thing here. What is truly horrifying is that there's no provenance. There's no way, if you do this accidentally, there's no way, A, to see that you've done it, and then there's no way to roll back. And I think that that's incredibly, incredibly dangerous. And there are plenty of examples of like real life data analysis, scientific papers where people have made these errors. Documents like the whole financial crisis is probably, 10% of it was like badly coded Excel spreadsheets. It's very, very difficult to see what's happened, to figure out how did you get to this result. And that, I think, is crucial to doing good science. So hopefully I've convinced you that you should be programming. Why should you use R? Well, so R is like, I'm not going to like sugarcoat it, R is like a quirky language. But most of the quirks, I think, are well thought out. Some of them are just admittedly like utterly bizarre. But some of the quirks, I think, are really well suited to working with data, to doing data science. So I want to talk about a few of my kind of favorite features of R. So one of the first one is that R is a vector language. So everything you work with in R is a vector. R does not have scalars. You cannot really work with a single number. This has kind of pretty serious performance implications. But the neat thing is you can express ideas very, very simply. Here I'm creating a vector by randomly sampling 10 numbers between 1 and 100. I can then say how many of those numbers are greater than 50, and I get a logical vector back. Right? And now there's no need to write a for loop here. I'm just going to apply this operation to this complete vector. And then I can say, well, I'm going to sum up this vector. When you sum up a logical vector, falses become zeros, trues become 1. So the sum of a logical vector is just the count of the number of trues. So this very simply and elegantly tells me how many numbers of this vector are greater than 50, 6 of them. Another thing that's really, really important when you're doing data science or statistics is the idea that some of the values in your data are going to be missing. You're not going to know what they are. That is the reality of working with real-world data, that some of the values are simply absent. And rather than just like omitting them, it's often actually important to track those missing values. And so R has missing values built in with this NA, short for not applicable. And what happens with missing values? They work very similarly to nulls in SQL. You get this kind of ternary logic. But basically, any time you have a missing value, that missing value is going to propagate in every expression. So here I've got a vector where I've just randomly rearranged the numbers between 1 and 5 and a missing value. And I want to say, for each of those values, is it greater than 2? Well, 1 is not greater than 2. Is a missing value greater than 2? You don't know. There's 3 and so on. Now, the thing that's a little bit weird about missing values is you might say, well, tell me what values in my vector are equal to a missing value. And if you do that, the missing values propagate and you just get missing. And this is a little bit confusing at first. Like, why does a missing value not equal a missing value? And I think you can kind of understand that by making it more concrete. So here we've got a variable that we use to store the age of John. How old is he? We don't know. And we've got another variable, typo in there, that we're going to use to store the age of Mary. How old is Mary? We don't know. Are John and Mary the same age? We don't know. Right? It's not like there's just one missing value, and if you knew that value, everything would be fine. There's like an infinite number of missing values, and there's no reason to believe a priori that any 2 missing values are equal. And so instead you have to use is.na, is missing alpha. So another thing that's quite unusual with R is that in one of the main data structures in the R language itself is this relational table, this data frame, or this tibble, basically this columnar structure where we've got variables that have names, and we get this rectangular structure. Here we've got a data frame with an integer, a character vector, and a real number, or a double digit. The other thing that I think is great about R, but I cannot really articulate why, is that R is basically a functional programming language. So R is not like Python, an object-oriented programming language. You do not generally solve problems in R by creating new classes and then instantiating objects from those classes. Instead, you tend to solve problems by composing functions in various ways. And one of the things that makes R a functional programming language is that functions in R can take functions as arguments, and they can also return functions as output. And it seems in some way, I think because generally when you're doing data science, there aren't a bunch of like different data structures. There's just one data structure, this data frame or relational table that you use again and again and again. You are doing different things to that data. The data is structured in the same way. You are doing different things to it, and functional programming seems to be a good kind of fit to that domain. The other thing that R does, it's quite different again, is that you can do a lot of meta programming with R. So this is a little snippet of R code that, like, I remember when I first encountered it as an undergraduate. I was majoring in computer science. I'd learned Java. I'd done PHP programming, and then I came to R, and it just seemed like the weirdest thing ever, because here, this plot, I'm plotting x and sine x, and when you look at the plot, it somehow magically knows like what the inputs to that function were. And now, like, this seems like utterly natural to me now, and if you've used R before, you may have never thought about this, but I still like vividly remember encountering this, and it just like blew my mind. It worked in a way that was very different to any programming language I'd previously encountered. And the thing that's neat about this is that R gives you an incredible amount of power to kind of look at the structure of code that you are working with. And so in R, like in every programming language, you can think about code as a tree-like structure, often called the abstract syntax tree. In R, like many languages with sort of a Lisp heritage, you can actually look inside that tree and manipulate it. So here, this is a function I've written actually called AST. It takes an R expression and it draws this kind of fairly nicely formatted like console visualization of what that tree looks like. And so we can actually, in R code, dive in to we can look at code, and we can introspect, and we can modify it in various ways. And the thing that I think is so neat about this is it gives us this sort of incredible power to create little domain-specific languages that are tailored to certain parts of the data science process. So this is what a lot of my work has been. My main claim to fame maybe is ggplot2 visualization package. Just provides like a domain-specific language for visualization. It allows you to express the relationship between variables in your data and aesthetic properties that you can assume. So I want to talk a little bit about that and talk a little bit about the so-called tidyverse, the sort of collection of packages that think about data in a similar way, that provide a similar set of APIs. And the kind of the theme that underlies all of these packages is this incredibly powerful way of solving complex problems, which is breaking them down into small pieces and solving the problem a step at a time. And I think this is a really powerful strategy for two reasons. First of all, it allows you to take little steps. And after each little step, you can check, like, have I ended up in a good place? If you're working with much bigger pieces, you might be wandering around for you're fitting some crazy deep learning model and it takes like a week of computing, and like a week later you're finished and you're like, I'm actually in kind of a bad place and I just wasted the last week. So whenever you can break a problem down into small pieces so you can get rapid feedback, that's an incredibly powerful tool. And the other thing that's great is because you've got these little pieces that you can recombine in different ways, often you can take pieces from one project that you're already familiar with, you understand how those pieces work, you can recombine them in a new way, maybe with a few new pieces, to solve a new problem. So it's much easier to generalize the solution from one problem to the next problem you encounter. So I'm going to show you a little example of a data analysis in R using some tidyverse packages. This is not my data analysis, it comes from Kyle Walker. Like an increasing proportion of my slides today, these come from Twitter interactions. And so this is using Kyle's package called tidycensus. So this is one of the neat things about R, because lots of people who care about data use R. There are a bunch of packages for getting data from various data sources, and as you might guess from the name, this gets data from the census. So I'm going to run some code. I'm going to get this data. So this is the type of data import that's just utterly boring, because it just works. And then I'm going to look at it. So here we have a row. There's about 520 rows altogether. Each row represents a statistical area. So it could be a micro statistical area, or a metropolitan statistical area. We have the name of this variable, which we've extracted from the census. I'm not going to tell you what that is, so I'm going to give you a challenge briefly to see if you can figure out what it is. Then we've got the estimate, and then we've got the margin of error, and some summaries about that. So one thing that's a little awkward with this is these names are kind of a little ugly, right? We've got, because of the way that the metropolitan areas work, they kind of aggregate big cities together in a region. So we have like Albany, Schenectady, Troy, New York metropolitan area, like it'd be nice to have the state in a separate column and so on. And so even when you get pretty nice data, you almost always have to do some data transformation. So I'm going to do a little bit of that here. I'm going to say, well, I only want to look at the big metropolitan areas, the areas that have greater than 2 million people in them. That variable is constant, so I'm going to get rid of it. I'm going to remove this metro area because it's just on every single column. It doesn't really teach me anything. Then I'm going to split it up into city and state and then extract those just so I get the first city and the first state and then do a little bit more cleanup. The other thing that's a little odd, which you can't quite see here, but there's this margin of error that has been recorded as negative 5555555, which is a little suspicious. And in fact, that is actually how this data is representing missing values. So I'm also going to turn those weird values into actual missing values. So when I do that, I don't expect you to read that code as I went through, but hopefully you can see kind of these major verbs. We're filtering, we're selecting, we're mutating, we're creating new variables, that we're expressing ourselves here with code. And when we do that, we get this nicer format. Now I've got the city and state, the estimate, and then I've got missing values here. And then I've combined these together to get me a simple city-state combination rather than that full, potential, massive, accurate metropolitan standard area. Then I'm going to plot that. Really, really good idea to always look at your data. Kind of my visualization rule of thumb is that the first visualization you look at will always reveal a data quality error. And if it does not reveal a data quality error, that just means you haven't found it yet. So I'm going to do a little plot. This is what the plot looks like. So here's the variable, like the estimated value from the census on the x-axis. We've got these cities on the y-axis. And what I want you to do is see if you can guess what this variable is. It might be a little bit hard to read, but the x-axis scale goes from 0 to 30. At the top, we've got like New York, San Francisco, Washington, D.C., Boston, Chicago, and at the bottom, we've got Indianapolis, Kansas City, Charlotte, Dallas, Tampa, Detroit. Any guesses for what this is? It's not population.
Cost of living.
Cost of living, that's
NBA.
NBA. Oh,
Basketball.
Basketball. Density is actually, I think, pretty close. This is the percentage of people who take public transportation to work. So New York, basically out there on its own, followed by San Francisco, DC, Boston. And so I bring this up to kind of illustrate these two plots. I think it's useful to think about like exploratory graphics, graphics aimed for you, the analyst, and the goal of an exploratory graphic is just to get the graphic as quickly as possible, get the insight, and then get on to the next visualization. And you don't need a lot of scaffolding because you're intimately familiar with this data already. But when you go to share this data with other people, it really helps to start thinking about good access labels, having titles and subtitles and sources that explain what's going on. And often, going from this to this is as much work as anything else. Now you've got to like get out of your own head. You've got to think like, what are people who have never seen this data before? What do they need to know before they can understand? And that communication part is so important in data science, so difficult to do, and I have no real advice about how to do it. But I wanted to talk a little bit about the sort of the thing that makes this, I think, easier. Like when you look at this code, like one of the things I think about a lot is not just the individual components of the problem, of the individual components of the programming context, but how do you join them all together? And I really like this quote from Hal Abelson, that it's not just the individual components that gives you the power, it's the glue that sticks them together. And so I spent a lot of time thinking about the glue. Like, how can you, once you've learned one part of the tidyverse, one package, how can we make sure that makes learning this next package a little bit easier? And I really like this idea of a pit of success. So you're probably familiar with a pinnacle of success, right? But to get to a pinnacle of success or a peak of success, you have to strive. You have to try really hard. The goal of a pit of success is you kind of fall into it by accident. And certainly, this is a little grandiose, probably are in the tidyverse, and more like a pothole of success currently. But this is very much my goal. I want to help you as data scientists get to the point where your fingers are just typing R code without you consciously thinking about it. And you can spend your precious cognitive resources grappling with the big questions of the data, not figuring out how to get the computer to understand what you're saying. But all that said, there are also things that are really hard to express with code. And I think this is a really simple example. This is a very simple scatter plot. When you look at the scatter plot, you might kind of say, well, these plots here look a little bit weird. These points here are a little bit different from the other ones. And it's really easy to say, whoop, these are the points I care about. But to express those points in code, are you going to figure out, well, what's the slope of this line, and then I'm going to carefully slice little pieces off. It's really painful. There are things that's very natural to kind of express directly on the data, but it's very tiresome to have to program. Another thing that I do a lot that's kind of painful is just sometimes you get a data set and the variable names are totally wacky and you have to rename them all. And doing that in code just feels sure you can do it, but you've got to copy and paste the old names and carefully type in the new names. It just kind of feels painful. That's something else, but just typing in a GUI just feels so much more natural. And I think one thing that's really exciting to me is now in RStudio, you can create these add-ins, these basically web pages that you can embed inside RStudio or the IDE. You can use that to interact with data in a way that feels more natural, but then you can generate the R code out of it. So I think it's fine, it doesn't matter, in some sense, I think a lot of, most of the code you will create by typing with your fingers, but some of it, there are things that are just difficult to express that way. And if we can create user interfaces that allow you to express those operations more naturally, that's great. Particularly if you can turn that into code, because then you get all of the advantages of code we talked about earlier. You get all this provenance, you get this reproducibility that's so important. I think there's a whole bunch of kind of other interesting questions, when we start working with these pipelines in code, maybe there's a typical, if you do a filter and then a mutate, can we predict what comes next? Can we prompt you, 90% of the time, people like you like this other function? Or can we do more with autocomplete? So I think autocomplete is a really interesting space where the primary mode of interaction is typing, but autocomplete kind of makes your life easier by giving you a bunch of options. How far can we take this? How can we help, how can we kind of guide you towards useful paths while still giving you the freedom to express whatever you want with code? There's also a bunch of really cool work about learning things from examples. I think learning regular expressions from examples is some particularly neat work there. Regular expressions, it takes a while to learn their language. It can be really difficult to kind of check that you've correctly generalized in the right axes. Can we just give the computer a bunch of positive and negative examples, and have it learn the regular expression for us. And there's kind of like easier, even crazier stuff, which I don't really know how you would use this, but there's this cool math pick service. You can take a photo of like someone's mathematical equation that's been tattooed on their arm, and MathPix will give you the LaTeX from that, so you can express that. So I think there's lots of like, what I believe in is like code as the primary artifact from a data analysis. But I think we've still got a lot to learn about how can we generate that code apart from typing it with our fingers. So to sum up, I think there's just so many advantages to using code over a GUI. It's just text, so you will laugh at copy and pasting and Googling for Stack Overflow questions are really powerful and effective workflows, but you also get this reproducibility, you get provenance with diffs, and being able to track what's going on over time. I think R is a fantastic programming language for data science. Yes, it's quirky, but a lot of the quirks turn out to be pretty good ideas and help you express data science challenges more naturally. And I should mention, like, when I say R is great, it does not imply anything about other programming languages. Like, when I say R is great, please do not take the subtext to mean that, like, Python sucks. Like, I think Python is great too, but I particularly love R. I really like this idea of domain-specific languages, figuring out how we can kind of carve out little pieces of the whole data science problem, provide little toolkits, little miniature languages that give you some degree of flexibility, that hopefully kind of like guide you into this pit of success, that hopefully success is a little bit easier, to a path of lesser resistance and failure. And then finally, like, while I gave you this very provocatively titled talk that you cannot do data science in the GUI, what I believe most passionately is that code should be the primary artifact. I think most of the time that you should be creating code by typing, but there's lots of scope for other types of user interface for also creating code. Thank you. I think we've got time for questions.
I work with a team at the University of Chicago, and we use R to make a lot of great things for nonprofit partners, kind of public and nonprofit partners, which they enjoy a lot. But when they do their own work on their own data, they like to use tableau. And it's, we make the case, but it's kind of challenging for them to kind of trust that they can make the investment. I was kind of curious what perspective you have in terms of the learning curve.
Yeah.
That's kind of good.
Yeah, I think there are two challenges. So first of all, firstly, there's this problem, right? Like, you haven't used R for 2 weeks and you open it up and this cursor is just like giving you the middle finger, basically. And I think that, like, if you are only doing data analysis occasionally, using a programming language is really, really hard because you kind of lose that, you lose all that context. Whereas with a GUI, the context is sort of encoded. Like, you can see what are my options. It's very, very obvious what you can do. So I think some of it, you do at some level you have to accept, there's a very wide class of people who a programming language is not going to be appropriate for. But there is also a large class of people who are doing data science every day, who I think can be very resistant to learning programming. And I think a lot of that is because programming just in people's heads is this really big, complicated thing. And I think if you could trick them into using R without talking about it being a programming language, that can help. And I think that the key is to find a few things that they can do much more easily in R, that they can express or elegantly, or like tedious things that they hate doing, and they've got to like point and click again and again and again, like they're doing their monthly TPS report, which involves copying and pasting like 15 different spreadsheets together, which is like an absolutely typical workflow for like thousands of people. Like if you can show them how to automate that boredom, like they will love you, and they will be like, R is awesome and I want to learn more. And then when they fail, as they inevitably will, because everyone fails when they're learning programming, there's like some light at the end of the tunnel to keep them motivated.
I'm learning R, and one of the difficulties I have is that when I get a mistake, an error that I have no idea about, and I Google it,
Yeah.
and it sends me to Stack Overflow,
Yeah.
and the page on Stack Overflow and several other pages on Stack Overflow with a similar error have nothing to do, are not recognizable to
Yeah.
me. The situations don't seem to be similarly the same. There's nothing like a log file that I can go to where it spells out, well, this is what's happening underneath the hood. And, warnings
Yeah.
don't always help, and traceback doesn't always help. How can you get past that? Because for me, I'm a magnet for situations like that, and that really stymies me and frustrates me.
Yeah, I think that is a big challenge. And one thing I kind of seems so obvious now, but I only realized recently is like one of the things that makes you one of the things that an experienced programmer can do that a newcomer cannot is look at these like error messages that look completely different, or like you see someone else's error message and the error message is the same but the situation looks completely different, and figuring out like how on earth does that relate to yours. Like that is like a tricky skill. I don't like concretely, like I think the way, like I think you need, like in some sense you need to find like a friend, or like you need to find a community of people.
Would you be my friend?
Yeah. You need to find like a community of people who can like struggle along with you. Like they won't always be able to help you, but sometimes all you need is like a fresh set of eyes. Sometimes, I think one of the challenges with the error messages in R is that R is like a very permissive language. Like you do something weird and I was like, okay. And you do something weird to the result of that and I was like, okay. And then 3 steps later I was like, hell no, I'm not doing that. And that's not actually where the error message is. The source of the error is actually like 3 steps. So, I mean, one of the things that, I think the other thing that I still have to do a lot of is just like do very simple steps and check that each step. Like the thing that I think it's easy to do is just do a whole bunch of stuff, and at the end of it you get this weird error message. And like honestly, I still do this all the time. I'm like, I've been programming R for 15 years. I'm gonna like write this function, I'm just gonna bang it out, and then it doesn't work, and I've got no idea why, and I just have to start and like do one step and then kind of look at the answer. One of the things that I've tried to do, and the tidyverse in particular, like if you use tibbles instead of data frames, like one of the things tibbles do is tell you the type of every column. Because if you have like a factor, if you think you're working with strings and you've actually got a factor, you'll get these weird error messages and it doesn't print out. So like finding tools that let you like figure out what the heck do I actually have, and is that what I expect, is really useful.
So you say shift it to a tibble.
So I think tibbles will help. The other thing, if you use RStudio, that's in the latest version of RStudio. Well, this is in. You like the view pane in RStudio. If you're working with weird lists, let's see if I can remember a weird list. That wasn't as weird as I thought. But now, like if the RStudio viewer can give you the ability to kind of drill down the environment pane and STR. Like I wish I had like a good answer for you, but some of it's just like, it's like pain and suffering.
What is your stance on versioning issues? I'm currently taking a class and I think I've probably spent a third of my time dealing with this package is not available for this R version. And there was a point today in class where I had 3 different instances of R, 3 different versions of R running in order to accomplish the task.
Yeah, that is something that is challenging. It's something that we've been thinking about a little bit at RStudio. I think one thing that you can often do is like when you install up packages, like with the blah package, say, oh, this is not available. Reassuringly. Often that means that there's like no binary version available, particularly if you're using an older version of R. And you can often say like type equals source and it will try and install. Just the way that CRAN works with kind of older versions of R is a little bit suboptimal. We've been thinking a little bit about how we can do better because that is a source of pain for us.
Sure. So in talking about the code being an artifact, what type of curriculum would you recommend for in the K-12 arena, and then for maybe artists who are trying to get into data visualization that have no programming or coding or very little statistics back?
So I've written this book for data science. This is kind of my attempt to kind of get you to the good parts of data science as quickly as possible. The goal of it is to be that you could come and read this book with no programming experience. I have not achieved that goal yet, but this is this is my attempt. I can give you there's a few other people that I would like look at. So Amelia McNamara is she's in the statistics department at Smith College. She also has experience teaching to high school students. I kind of think the key thing is how do you show them the light at the end of the tunnel? Like how do you figure out the shortest path to something that they think is awesome and useful? And if you can do that, then you build everything else around that. Right? You figure out what is the shortest possible path to get from knowing nothing to doing something awesome. Like, don't worry about the theory, don't worry about anything, just worry about how do you get them to do something cool. And then once they can do that, then they've got the motivation to like struggle through some of the inevitable pain.
And what about for artists? So you have artists who would get a job in
So artists, again, it's like finding that motivation. So one person has done some cool, I always forget his name, Thomas Peterson, has done some kind of cool artist stuff. He's got a bit I can show you, he made the most horrifying picture of me at university. Let me see. So he's done some kind of cool, finding cool, things that hook people's interest, I think is neat. He's also done stuff like exploring how deep learning, how can you visualize what a deep learning model does. Oh yeah, this is the horrifying picture of me. My face doesn't peel off like that.
It's like,
But it's kind of this stuff that's fun, thinking about how you make these animations. I think is a neat way of an in for artists. And then you show them how do you do stuff that you're interested in, and then sort of walk them towards other stuff. I don't have any specific advice. That's just kind of my
Oh, that sounds good. Thank you.
With your university work, what kind of trends are you seeing with the students coming through now? Right? People just now doing it.
Like my university work is like structured in such a way that I do as little university work as possible. So I can't kind of speak too broadly to that. I think sort of broadly the trend, like to me, like the trend that is the craziest is people are coming out of high school and they are excited about statistics and data science. Like, 10 years ago, you'd have like 4 statistics majors who like came out of high school and were like really excited about statistics. And now you've got like 150 people who are passionate about it. I think that's the biggest difference. I don't see, like in terms of the kind of the skills like coming in with, I don't think that's changing profoundly. Just because I think like, people are more familiar with like computational artifacts like iPads, but they're getting less idea about how they work behind the scenes. There's still a lot of like, how do you like kind of unpack these like beautiful manufactured objects and then start. I think one thing that's like, 10 years ago, you could start programming and you can create something, your first attempt does not look that far away from like state of the art. But now, like your first app is not going to look like a really polished iPad app. And in some sense, the distance is far away. And kind of making like, how do you kind of help them like get over that? Like, my work looks like shit. Which is sort of in some sense like the challenge of the internet. Like no matter what you do, you can find someone on the internet who does it 10 times better, right? And you've got to like figure out some source of motivation other than being like the best person in the world.
Yeah, this idea of a fit success is really interesting. You mentioned a little bit about how to call it. Can you talk a little more about other things different as developers can do just with personal habits to try to fall into fit success?
So for developers to like dig the pit for other people to fall in, or to fall in yourself?
I just started falling myself, and then I can get myself, and then maybe I can drag some other people down.
You can pull them in with you. I think like the thing like that sort of throughout my career has been like most sort of successful in that is like deliberately carving out some time like every day or every week where you are focused on not like solving the problem, like your short-term problems, but thinking about like what are things I need to learn about like that are not going to pay off today but might pay off in a couple of weeks. Like explicitly like seeking out new things to learn and to master. I think one trap that is easy to fall into if you do that is that like if you follow Twitter or you read blogs or Hacker News or whatever, there's just like there's all these like amazing things and you're like, wow, this is cool, and this is cool, and this is cool, and then you end up just like spending. So there's some like you also have to like invest deeply in something, I think. And you have to have like at some level just like ignore all of these other amazing things that are going on and just kind of focus and keep on like, digging your pit a little bit deeper.
I want to thank you on behalf of our users everywhere for dplyr and readr+2. These are the main ones I've used. Really is about packaging. So the power of R, in some sense, is all the expertise that's gone into 4,000 or whatever the number is now, 10,000. However, they tend to be kind of islands of design space, and the way they're structured, they're very difficult to use as a casual user.
Yeah.
You say, I'd like to put these two ideas together, but I can't connect the dots. So with your expertise at taming that kind of connectivity problem, what do you see as a way forward to help expose these things?
So I think part of that, like, that problem is never going to go away. Because I think, in some sense, like the best and worst thing about R is that most R users are not programmers. And that is awesome because just the diversity of people using R is incredible, and it gives a very, very wide range of people to help understand their data. But it also means that like most people writing packages have never had any formal training in software development, and that can lead to some badness. Like kind of my goal, I think, is to sort of figure out, it often takes me a long time to like sort of externalize the things that I believe about code, or the ways that I think you should structure code. And so like one of the things that I'm thinking about sort of slowly more and more is like, now we've got the tidyverse, now we've got a collection of packages that fit together pretty well. Like why do they actually fit together well? Like, what are the properties? And then like how can you use those ideas in your own code? So currently that's kind of at the phase where I'm like giving workshops every now and then where I'm sort of talking about that and slowly refining those ideas. But my sense is like that is the next book that I want to write. R for data science is about like how do you do data science for R. Advanced R is about like how does R work. Packages about how do packages work. But I want to write a book that's like how do you like take this big messy problem and decompose it into small functions that work well in isolation, that kind of heave to existing principles, that mean they kind of fit in more naturally to a broader ecosystem. But like, I feel like I can barely do that myself, and it takes me a long time. And like figuring out how to explain to other people that's the journey, which would take several years, but I think is really important.
Talk a bit for the end about examples of like interacting with your data more directly and exposure to not directly. Where are we right now in terms of what's currently available and what's the roadmap
Kind of at like the ground floor, I would say. I don't know, like I think a lot of the coolest kind of work with like, I don't know, we're kind of, I would say we're like in the 1980s currently. One thing that I think is really neat is the statistical computing section of the American Statistical Association has this video library, which has a bunch of videos of like interactive tools that people developed. So this is like one, this is like Tukey, this is like Jerome Friedman, like developing these interactive tools. And like the sophistication, but they had like rotating 3D displays and light pens in like 1973. Now, admittedly, this is like at the Stanford Linear Accelerator, which is like the biggest and most powerful computer in the world probably at that time. But in some ways, like I think we're still like the golden age of kind of interactive statistical graphics. I think was the 1980s, and a lot of those tools we don't have to hand today. But particularly then, like turning what you have described with directed manipulation into code, there's very little there. There's sort of some interesting work in the CS Infobase community and VAST community. I think they're still sort of getting their toes in this water as well.
So one of the complaints with R is that it cannot be used very easily in production environments. So what's your roadmap for that?
Yeah, that's sort of a hard question to answer because like what a production environment is varies over massively. Part of the problem is that just R is unfamiliar. Like most people who are running production environments have a traditional software engineering background and they're very, very comfortable with Python. So part of the problem is just educating those people, like, yes, R is a real programming language, and sure, people can write really crappy code in R, but they can also write really good code as well. So there's a little bit of that. There's also just because, again, like R is a community that does not have many kind of full-time software developers in it. There's some pieces of the puzzle that are missing because no one in the R community is that interested in them yet. One of the things that sort of made me excited to join RStudio was to have this company that can hire full-time software engineers to work on a lot of this sort of boring infrastructure stuff that no one wants to develop out of the goodness of their hearts. So I think we're starting to see that. Some of the things, they're not directly production related, but like Sparkly R, we now have a pretty nice interface for talking to Spark from R. We've also invested a lot. There's just there's a bunch of sort of R in production problems. It's just utterly kind of boring infrastructure, and so we've also invested a lot in databases and how can you have performant, safe, correct connections to databases, and just over time we'll slowly as we find out about them knock off more and more of these problems that we I think R is always going to be higher friction to put in production because again most R users are not software engineers, and that's a strength and a weakness.
This is kind of a random question, but within RStudio, how can I explore the source code behind some packages, see what modules are in there, what functions are in there?
So pretty much everything, well, not everything, but the vast majority of what RStudio does is on GitHub somewhere. So even the IDE, there's a few main organizations. So the RStudio organization, that's where the IDE lives, that's where Shiny lives. There's also a tidyverse organization where all the tidyverse packages live. You can just go in and dive in and see what we do.
So I'm studying data science and got some courses in R and some courses in Python. So I'm learning kind of a little bit of do you think that's good, or in the future I should choose a language and stick to it, or it's good to know a little bit of
I think it's good to be able to read and have a basic understanding of both Python and R code. But I think you're better off specializing in one. You're better off going deep in one and mastering it. You don't just want to be you don't want to silo yourself. You want to have a sort of a fairly broad but shallow understanding of other things. But I think generally it's you want to master something so you can be really, really good at that rather than sort of spreading your expertise too thinly. And because often I think when you go deep, if you go deep into R and learn about how the language works and functional programming works, when you go deep in a language, you do learn these ideas that then you can translate to other languages. You can take what you've learned about functional programming in R and then eventually translate that to Python. But if you never kind of go deep enough, you never build up that strong enough mental model that you can transfer.
I think purchasing R migrating over to medical research, pulling this data and stats from the hands of the doctors that are used to that. And the conversation that I'm sure you see on Twitter about reproducibility across research and opening up data sets, I wanted to hear your thoughts on the thing about Shiny documents and R Markdown. LaTeX is a high barrier to entry,
Yeah, and I think that's like that is like one of the explicit goals of like the R Markdown project. That you write in the standard format and then you can export to like Word documents if you need to. It can generate LaTeX and PDFs. It can generate the HTML. And then the thing about like R Markdown and Markdown in general is that it's like it's sufficiently simple that you sort of don't have to worry about it going away. I think like you can sort of re-implement it if you like first of all like it's not a binary format. So you can always just like read it in plain text, and it's not the best thing, but you can still see all the data. And then like the other thing that I think is really good practice, like Jenny does in her frogs data set, is you don't just save the source code of everything. You also actually save the rendered documents. And saving, so like when you have an R Markdown document, saving the rendered Markdown is actually really useful because you can actually see the data in here. And then like if it's checking this into Git and your data changes, now you get a diff and you see exactly what changed, not just with your code, but with the inputs and outputs as well. And then that means like having these kind of multiple layers means it's more likely that you're going to be able to recover something in the future.
Yeah, so you're talking about Markdown. I'm poor, so a lot of times I can't buy the book, but I would like a PDF. And I know that a lot of the authors do things in Bookdown where you can render it, but the PDF document has been disabled, and it defaults to HTML. But my question is, a lot of the times it fails when I try to render it in PDF, is that it fails on the Pandoc chapters. And I can't find where to change it because there's always the error message. And I want to know, is that on purpose, and I should stop and just accept the HTML that I'm offered on the Bookdown site, or?
I think part of it is like fundamentally like creating something that works with both HTML and a PDF is like more work, and it's easier to just disable one. So that's what I do, and then when I go and actually when I send the book to the publisher, that's when I actually go and make that easier. And like that is like a lot of pain and frustration for me, and I don't want to do. I could make that frustration go away by doing it more frequently, but I don't want to. So I don't think there's any there's typically no kind of I don't think there's any sort of deep philosophical objection. It just feels like you can always print an HTML into a PDF and turn that into a book somehow. Yeah, but it's.
But where's the Pandoc? Well, my question is, where's the Pandoc? It produces a LaTeX command with the Pandoc that incorporates Pandoc. Where is that stored so that I can follow that error message and just make that change?
It should just be in the directory of downloading. But maybe we can talk about this. We'll take one more question. Okay.
So you talk about simplifying these kind of broad principles into more succinct, abstract, smaller chunks. If you keep abstracting back, you're going to end up with a GUI in itself. And you, I guess, kind of started doing that with RStudio and the add-ins. At what point are you satisfied, or do you just end up with another pipelining program like Mime or Orange?
I don't know. There's something. I really dislike those kind of pipelining programs where you solve a problem by dragging things together. And I think I dislike them because what they try and sell you is that the hard part is typing the code. The hard part is not typing the code. The hard part is figuring out which input should be connected to which outputs and which components you need. And Nime and there's a bunch of SAS enterprise data modeler or whatever it's called does something similar. They just don't seem they don't make the problem that much easier because you've still got all this flexibility, but because you don't get code, you lose benefits of all the like code tools that like software engineers have spent the last 50 years developing. So they just sort of feel this like awkward, like uncanny valley, like they make a problem, they make the easy problem easier and make the hard problem harder.
Thank you. Let's thank Hadley for